Hello everyone, my name is Flavio Arrais and I'm going to talk about a design of stainless steel elliptical hollow section columns in case of fire, a parametric study, a research work performed at the University of Aveiro. This presentation is structured by the following topics, starting with a small introduction with general concepts about stainless steel under fire. Then I will talk about the fire resistance rules presented on Eurocode 3, part 1-2, also presenting a proposal for stainless steel columns at elevated temperatures developed particularly for high profiles that were analyzed for this study. About the numerical study, I will show you the different case study analyzed and the performance of the numerical model. After that, I will present some numerical results obtained and the comparison with the Eurocode 3 and the other proposals with the statistical analysis. Finally, some conclusions about this work to finish the presentation. Starting with the introduction, the use of stainless steel in construction has been increasing due to different qualities like durability, resistance to corrosion, and aesthetic appearance. Also, it has higher fire resistance when compared to carbon steel, allowing in some cases the absence of thermal protection. The most common stainless steel grade is the austenitic, but recently some interest has also been shown for the use of ferritic and duplex steels due to the specific advantages like the lower percentage of nickel of the ferritic grade, which reduces its price, and the good resistance to wear and stress corrosion cracking of the duplex grade. This research is about the elliptical hollow section stainless steel columns at elevated temperatures. Elliptical hollow profiles presents a nice aesthetic nature, have different structural advantages, and considering the stainless steel material, it seems to be an interesting option for design. Also, the elliptical hollow profiles have better torsional buckling behavior than open sections and a greater bending strength than circular hollow profiles. With the Sapphire Finite Element software, elliptical hollow section stainless steel columns are numerically analyzed for one austenitic stainless steel grade known as 304, one ferritic, and one duplex, and obtained ultimate load-bearing capacities compared to the Eurocode 3 design methodologies and the different proposals for high section columns in case of fire. The buckling mode shapes were obtained with the software Cas3M and applying the interface Ruby to define the initial geometric imperfections. About the fire design rules. According to Eurocode 3, it is necessary to classify the cross-section to evaluate the cross-section slenderness. However, there is no specifications for elliptical hollow sections in the current Part 1-2 of Eurocode 3. Therefore, according to previous references and researches, here are presented the recommended limits to classify elliptical hollow sections under compression and the equivalent diameter for columns. According to Part 1-2 of Eurocode 3, the design buckling resistance of stainless steel members subjected to axial compression should be verified by satisfying this expression, calculating in the same way as for carbon steel, changing only the mechanical properties of the material. The design resistance value of actually compressed members of class 1, 2, or 3 cross-sections with a uniform temperature is determined from this equation, where the stress corresponding to 2% of total strain should be adopted as the yield strength. For class 4 sections, the effective area should be considered instead of the gross cross-section area. And according to Annex E from Part 1-2 of Eurocode 3, the proof strength at 0.2% strain should be used. The cross-section resistance was obtained with the numerical models from Sapphire and considered. The reduction factors are given on Annex C of Part 1-2 of Eurocode 3 for stainless steel at high temperatures for the different analyzed stainless steel grades. Considering Lopes et al. Proposal for axial compression stainless steel high profiles in case of fire, the same procedure is performed, changing only these parameters. The accuracy of the application of this proposal for stainless steel sections was tested in this work. Also, considering Kukukler et al. Proposal, the same procedure is performed changing these parameters. Also, considers the use of the stress corresponding to 2% of total strain as the steel yield strength also forecasts for cross sections at elevated temperatures, as it is done for the remaining sections. And the accuracy of the application of this proposal for stainless steel section was also tested in this work. Now presenting the numerical study at each stage of its development, elliptical hollow section stainless steel columns for these 12 different cross sections under 4 different high temperatures were considered and restrained on the minor axis or on the major axis. The choice of the temperature of 350 degrees is related to the recommended critical temperature for profiles with class 4 sections when no calculation is made, being the other temperatures chosen for being common critical temperatures in this type of structural elements. Different members' lengths were also analyzed with lengths between 1 and 15 meters, considering this slenderness range. For these 3 stainless steel grades and considering the temperature uniform throughout the cross-section. Shell elements with 4 nodes, with each 6 degrees of freedom, 3 translations and 3 rotations, applying the finite element software Saphir were considered. Hinge conditions were applied at both ends, preventing lateral displacements throughout the member length and at midspan, preventing the longitudinal displacement to ensure the element and load symmetry. The loads were applied parallel to the element axis at the member extremities, distributed over the cross-section surface to avoid the local instability phenomena. The end plates were at normal temperature and had 10 times the thickness of the element's wall. The stainless steel stress-strain relationships here presented were taken into account in this study for the vanishing at temperatures and stainless steel grades. Geometric imperfections were considered with the buckling mode shapes obtained with CAT3M and the Ruby interface. The amplitude of the geometric imperfections were 80% from those recommended by part 2 of EN 1090 and by part 2 of EN 10 219 according to part 1.5 of Eurocode 3. Also, according to part 1.5 of Eurocode 3, to combine these different geometric imperfections, a leading imperfection should be considered with the total amplitude and the accompanying imperfection with 70% of its value. Now presenting the numerical results. Here is the analysis for the austenitic stainless steel. From the results of the charts, it can be observed that for small and intermediate slendernesses, the Eurocode 3 is not safe for a large domain of the results of the austenitic stainless steel. Considering Lopes et al. Proposal, the results are always on the safe side. However, the buckling curve is too conservative. In the case of the ferritic stainless steel, the same is also observed for the temperature of 700 degrees. This difference on the results at 700 compared to the other temperatures is due to the abrupt reduction in the reduction factors set out in Annex C of Part 1.2 of Eurocode 3 for temperatures above 600 degrees. In this stainless steel grade, once again, with Lopes et al. Proposal, the results on the safe side are on the safe side. However, the buckling curve conservative. In the case of the duplex stainless steel, the results are on the safe side compared to the Eurocode 3 rules. However, this buckling curve is slightly conservative in almost all the results. Lopes et al. Proposal is safe, but it is always too conservative. The proposal of Kukukler et al. Showed some improvements compared to the actual Eurocode 3. However, the curve is still out of place for these elements with this type of cross-section, where it is possible to have both results on the safe side, as well as outside the safe side, and in some cases the proposal curve is still too conservative, clearly showing that this proposal was not developed for elliptical hollow section columns, but for eye-shaped profiles. Here are presented examples of different collapse modes for the analysis around the major axis and around the minor axis after completed the numerical analysis. For a detailed analysis of the obtained numerical results, a statistical evaluation of the methodology is here presented, following the three criteria of the validation procedure proposed by Krupa. From the results presented in these tables, it is possible to conclude that when comparing the numerical results with the Eurocode 3 fire design rules, many of them are on the unsafe part, with a high percentage of unsafe results. In contrast, Lopes et al. Proposal for eye sections shows few unsafe results. However, this design curve is too conservative. In the case of Kukukler et al. Proposal curve for eye sections, it can be concluded that it is not well adjusted for the resistance values, resulting from stainless steel profiles with an elliptical section, as is visible in this chart. The presented tables are also shown the obtained statistical values for each analytical curve, but considering the results for the minor axis. And from the results presented, it is possible to observe the same conclusions obtained from the analysis of stainless steel profiles, actually compressed around the major axis. From the main conclusions, this research presented a numerical study on the fire behavior of actually compressed columns, with elliptical hollow section of different stainless steel grades, considering different profiles of different cross-section classes, analyzed for different elevated temperatures, considering the buckling in both directions of their main axis, concluding that the fire design part of the Eurocode 3 does not provide adequate and safe methodologies. A proposal developed by Lopes et al. Was also analyzed, and it was concluded that the application of this proposal made it possible to overcome the insecurity previously observed with Eurocode 3, but in a too conservative way. Also, a proposal developed by Kukukler et al. Was analyzed, revealing that this design proposal is not well adjusted to this kind of cross-section shape. As a main conclusion, the resistance of stainless steel structural elements with elliptical hollow sections subjected to fire is not well yet fully clarified, thus motivating and justifying the development of further studies aiming to achieve more accurate and safe formulations for these elements. And thank you very much for your attention.